Okay, so we're going to take care of velocity time now. In the past couple days, you've been thinking and talking about distance time or displacement time. Okay, so these guys I will commonly refer to as VT graphs. That's how I say it, VT graphs. Come on. There we go. VT graphs. That's all we're talking about. VT graphs. So what does that mean? You're going to have velocity on the y-axis and you're going to have time on the x-axis. That's all it is. Okay? Yep. Yeah, that's graph. Okay. So uniform motion is what we've been talking about in the past. And we're going to continue to talk about that, but we will also introduce non-uniform motion. So again, uniform motion, acceleration is 0. The picture that they're showing us here is a graph of velocity versus time. It's in kilometers per hour and hours in the x-axis. So just by looking at the graph, what can you tell about the graph? Is the y variable changing? Is it? So the velocity is remaining constant. So right here you can see v is constant. The velocity is not changing. If you're driving the speed limit in your car going to school or going to work or something, and you're just going 60 the whole way, is your velocity constant? Yes. Are you accelerating? No. So this would be an example of uniform motion. No matter what the time is, as time progresses, the velocity remains unchanged. All right. Let's take care of this first box, or this first point. Determine the slope. What does it represent? Okay. How to determine the slope of a line? Well, you need 2 points. Let's use these 2 points. Help me find the rise. What is the rise? The change in the y variable is 0. The change in the y variable is also the change in the velocity, which we know is 0. Because the graph is not rising or falling. What is the change in the x variable, which in this case is t? Sure, let's do the 1 hour, like the point I have. All right, let's take a look at this result. What is 0 divided by 1? 0. More importantly, let's take a look at that unit. You have kilometers per hour in the top, and you have that per hour. So you have kilometers per hour squared. Kilometers per hour per hour. That's what that means. Kilometers per hour per hour. What unit is that? You might recognize this one from physics or from science 10, meters per second squared. That's acceleration, right? Does it make sense that our acceleration is 0? Yeah, we talked about that already. So what does the slope of a VT graph represent? It represents acceleration. In other words, the change, rate of change of the velocity. It's like, to what degree is the velocity changing? Is the velocity changing quite rapidly? Or is the velocity not really changing at all? Okay. Now, if you just go back to my whiteboard, all we cared about for constant velocity, for uniform motion, all we cared about from the graphs is the slope. That's all we cared about. When you start getting to the VT graphs and when we get to acceleration time graphs, we actually care about one more thing, and that's the area. So the area under the graph is actually connected to something in calculus, where all this physics comes from. So Newton, when he was avoiding the plague in, I think, the 16 or 1700s, he single-handedly developed calculus by himself, alone, to explain his physics. And part of the calculus is determining area under curves. Now for us, we will only determine area for shapes we understand, so rectangles and triangles and stuff like this. That's all we will calculate areas of. And just by taking a look at the units of the area, we can decipher what it represents. So let's go ahead and calculate the area of a section. Let's use the same points, and let's calculate the area under this curve. Let's calculate the area under that curve. Now, what shape is that? A rectangle. So you know that the area of a rectangle is which formula? Base times height, or length times width, whatever you want. And in this case, the length is what unit? Hour. And the width? 900, and the unit? Kilometers per hour. Okay, and what do you notice about the units? The hours cancel, and you are left in what unit? Kilometers. This, good. This is distance or displacement. Take a look at the graph. What do they have right here? Displacement. So the area under a VT graph, what does it represent? Displacement or distance, depending on your y-axis. If it's speed, it's going to be distance. If it's velocity, it's going to be displacement. So typically it's velocity. Okay, so these two bullets, highly crucial to your kinematics success. The first unit A, kinematics, you got to know these two things. And if you forget, it's easily derived just by looking at the units. Like, look how I did that. If you forget, or I didn't study, or whatever reason, it's easily derived to just look at the units. Even for the slope. When we did the slope, you can just take a look at the units. Kilometers per hour, and that's an acceleration unit. This is an acceleration unit. All right, non-uniform motion. Non-uniform motion, what does that imply? Acceleration is not zero. Acceleration is not zero. If acceleration is not zero, that means it's accelerating. If you look at the diagram, top right, you have a ticker tape. I'm gonna attempt to show you guys the ticker tape. All it is a spark timer. So that's these guys here. You plug it in. It's got a little circuit board in there. It's got these copper electrodes, and you put through this carbon paper, this stuff. You might have seen this in Science 10. It goes in here, and then as the paper is traveling through the spark timer, this produces a zap. It produces a zap of electricity every, has the same frequency. It just does it every, maybe it's 10 times per second or whatever. And then from that frequency, you can calculate time. And however fast that thing is moving through the spark timer, you can determine what type of motion it is. If you look at this spark timer, look at the dots Are they equally spaced out? No. And that's all you got to check. If they're equally spaced, it's uniform motion. Uniform motion because it would, in the same amount of time, it would have the same amount of distance. Same amount of time, same amount of distance. Okay? So you guys can sketch that in. I'll have you do that. So just draw a rectangle. And just draw evenly spaced dots. If you saw that, you would think uniform motion. That's what you would think. But if you see the dots that I have there with the blue, you would think non-uniform motion. So like I said, and it's might be confusing at first, but each dot occurs at the same time interval. So in one interval, you travel that far. In the second interval, which is the same time, you travel that far. And then in the third interval, same time, you travel that far. So what is it saying? You're covering more distance in the same amount of time, each interval. So you are, in fact, speeding up. You're speeding up. If you were to look at a table of values, as delta t changes, or as t changes, it looks like delta t is 1 second. Every 1 second interval, look at the distance covered. 2 meters in the first second, but in the second second you covered 6 meters. For it to be uniform motion, that would have had to been the same number. For uniform motion, it's 2, 2, 2, 2, 2, after 1, 1, 1, 1, 1 in change. So this is another way to identify non-uniform motion. And you can keep going with this pattern. The next one is 10. The next one is, what was that, 14? And then what's this one? 18. All right, so another way to tell if the graph is, or if the situation is non-uniform motion, is the graph. This is a graph of what's called a parabola, P-A-R-A-B-O-L-A, parabola. This is studied extensively in Math 20, whether it's -1 or -2, both of those cover that. The parabola is actually a U-shaped curve. The parabola, like y equals x squared, it's actually like a U, but because we are not interested in the negative time, you don't see that. It's part of the graph. All right. And then bottom here it says, what does the slope of the graph indicate about the speed of the car? So how do you find the slope of something that's curving? So what you would do is you would take a point on the graph, like right here, and what you would do is you would take your ruler and you would attempt to draw a line that just touches once. And then you would call that a tangent line, and you would find the slope of that line. You could do it again, maybe right here, and you would find the slope of this tangent line. And you could do that for a bunch of different spots, maybe up here now. just want your line to touch it, just touch the curve just once. Those are called tangents. So if you had a straight edge or a ruler or an ID card, you could try to draw a few of those in. And if you take a look at, just by looking at it, you don't have to do any calculations, compare the slopes of those lines. Are they getting steeper? They are getting steeper. So what could you say about the slopes? The slopes are increasing. If the slopes are increasing, what does that tell us about the physics? Well, first of all, what's the unit in this case for slope? It's a position time graph, so what's the unit for slope? Delta y and delta x is going to give you meters per second. That's a unit of speed or velocity. So if those slopes are increasing, what can you say about the speed or velocity? It is also increasing. Okay, so hopefully as I talk, you are jotting stuff down. Please don't just sit there idly. Please be taking down notes. Alright, so all that stuff I just put on there, I was nice enough to copy it down for you. So I guess maybe you don't have to put notes if you don't want to, but I recommend that you do. Okay, let's talk about two distinctions to be made for velocity. You're going to have two types of velocity. Zach, can you just please stop? You have instantaneous and you have average. Average velocity will be the secant line, and instantaneous velocity will be the tangent line. Okay, let's just think about a situation. You're in your car and you're driving to school. Or you're on the bus and the bus is driving to school. You start, you slow down, you speed up, you stop at a red light, the light turns green, you start again, you drive the speed limit for a while, you slow down for a car, you speed up to pass a car, okay, and then you drive to school and you stop. Look at the blue curve. Do you see the blue curve? It's constantly changing, right? You can think of your speed as pretty much always changing. You're not always going the same speed. Do you guys agree with that? Yeah. So, if it took you 10 minutes to get to school, and then you knew the distance from your original place to your final place, you could find your average velocity. Does the average velocity tell you anything about what your speeds were in those moments? No. So that's this one here. Instantaneous velocity. This is speed in a moment. And you can see that the tangent line will grab the speed at a moment. It's at a particular point, and you have to graph a tangent. A tangent touches once and once only. Whereas the secant has a starting point and an ending point, and then you draw the line that connects the 2 points, and this is an average speed, okay? Maybe the speeds are a little bit different here, 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 but that secant gives you the average of all those different instantaneous speeds. Another way to think about it is that think of like Usain Bolt when he does the 100-meter dash. When he starts, is he going his top speed? He's speeding up to his top speed, right? Then about halfway, he's probably near his top speed, and he's going so fast. Roughly his top speed. So hopefully in the homework you saw that question. You guys remember that one? Hopefully you saw that in the homework. That question there talks about instantaneous versus average. Okay, and this diagram here was what I was talking about, calculating the various speeds. Calculating the various speeds at different moments. These are slopes of tangents, slopes of tangents, slopes of tangents at various points. And you can see that these lines are getting steeper. So that's exactly what I already talked about. And you notice all that stuff comes from the textbook. So you should also be reading some stuff in your textbook as well. So just a word on me, I don't use the textbook like directly. I don't say, hey, go to this page and read this. So please, on your own time, be reading your textbook. Okay, this has been a while up here, so I think we only have, let's just rip through this. Okay, a ball is bounced from the second story of a building. The displacement of the ball is shown below. Determine the average velocity. Okay, so circle this word. Put secant, and I'll have you guys actually do this rather than me. You're going to connect time 0 to time 4 with a secant line and calculate slope. Go ahead and do that now. The solution, I think this one's quite obvious. As 1 second goes by, you displace 1 towards the origin. So the slope of that line would be, 1 over 1, which is 1. And the sign is negative. So -1, and the unit is meters per second. Now this is where some students get a little bit confused. When a ball is dropped from a building, does it have constant speed? No. Look at the curve, the blue curve. Is the blue curve linear? No. So the speed is changing. Okay, so what we just calculated is an average velocity, okay, for that time frame. It doesn't mean that the ball is traveling that speed all the time. Keep that in mind. Okay, go ahead and do the next 2 bullets. Should be quick. Yeah, good. So from the time interval 4 till 7, that is going to be linear motion somehow. So this is linear, even though on the bounce it shouldn't be, but they're telling us it is, so we'll just go with it. Calculating the slope of that line, you can see it's positive 1 meter per second. This time because the slope is up to the right. Over 1, up 1, whereas this one was over 1 and down 1. Now how about the average velocity between 0 and 7? So now, what do I connect? What do I connect? Beginning to the end. Good. Go ahead and do that now. Beginning to end. Now what's the average velocity on that line? You can see that it's down 1 and over how many? 7? Rise over run? -1 over 7 meters per second. You guys okay with that one? It's down 1 and over 7, rise over run. Okay, now let's try the very last one. And this is where we got to be careful with our reading. And when you're doing this on the test later, you have studied the difference between instantaneous and average. We want the instantaneous velocity at 2 seconds. So find 2 seconds and put a dot. And then you have to draw which type of line? Very nice, tangent. And I'm thinking we have something like that. Now to find the slope of this tangent, I'm going to use 2 points on the line that line up quite nicely with the grid. And you can see at that point in particular, it looks like it's the same as the average over that interval. Over 1 and down 1, it looks like V instantaneous is -1 meters per second at that spot. You guys agree? Over 1, down 1? All right, so that's the difference between instantaneous and average. This is a summary page, so you can put the word summary here. Get some interference, eh? You guys hear that? It's my phone, I think. Come on. We're having a little bit of lag here. This worked example is exactly that. You don't have to do any work. It's already done for you. So you have a VT graph showing positive acceleration. Positive acceleration. Why is it positive acceleration? Because the slope is positive. The next one is negative acceleration. Why? Because the slope is negative. Remember, rising to the right, falling to the right. And the last one, the acceleration is 0 because the slope is 0. Any questions about that? That's some Math 10 review, some Science 10 review. So this try on your own. You can try this. And then there's the assignment. Only 4 questions. Okay? Only 4 questions. So we'll revisit this try on your own in a little bit.